look at this chart that you glued into your notebooks.
Are you recording this?
Yes.
Is it recording right now?
Yes. It's been recording this whole time.
Wow.
Which is why you need it. Okay. So, we're on page 2 of the notes part, okay? And we got to talk about these periodic trends. So you should already have these notes written down from the Fusion page, from the PowerPoint, from the Fusion page. But the first thing I want to talk to you about is electronegativity. And my slide doesn't have electronegativity. It has this thing that says electron affinity, but it's very similar. Yours has it, mine doesn't. So, what electronegativity is, right, is the ability of an element to attract an electron, right? So, this trend increases from left to right on a periodic table and from bottom to top on the periodic table. And that makes sense because these elements over here, okay, they're trying to lose electrons in order to achieve stability. So they have a low electronegativity. But as you go across the periodic table to these elements over here, especially fluorine, which has the highest electronegativity, they're trying to gain electrons. They only need one electron in order to become stable. Okay, so they have high electronegativity. It's relatively easy for them to attract electrons because of this high electronegativity. The reason why it increases from bottom to top is because these elements down here, their valence electrons are pretty far away from their nucleus, so the pull on those valence electrons is a lot less. Up here by fluorine, there's only 2 energy levels that separate the nucleus from the valence electrons. So the nucleus has a really strong pull on those valence electrons. So it's easy to capture an electron and pull it in when you have very few energy levels. It's kind of similar to like if you take 2 magnets. The closer they are together, the more you can feel that magnetic attraction, but the farther you pull them apart, the less you can feel it. That's exactly what's happening here with electronegativity. Okay, the closer the electrons are to the nucleus, the harder the pull. Okay, so that's what that's all about. The next trend is ionization energy. So ionization energy is how much energy it takes to remove an electron from a shell, from an energy level. Okay, so ionization energy increases from left to right, just like electronegativity, and it also increases from bottom to top, just like electronegativity. So that makes sense, because again, these elements over here are trying to get rid of electrons. So it's not going to take much energy to pull one off of these elements in group 1 and group 2, and even over here by group 13. But as we go across here, these elements are wanting to gain an electron. So they're holding all the electrons that they have really, really tight because they just have like 1 or 2 left to gain. All right, so the ones that they have, they're holding on to them really closely. It's kind of like when you guys were playing electron bingo, and you only needed 1 more to get a bingo. And if somebody came by and like messed up your card, you were really mad, so you were kind of protecting it and holding it really close so that if I called the configuration that you needed, you'd get bingo. Because all you need is 1 left. That's the same thing that's going on over here. Okay, they're only 1 away. Right? So that's ionization energy. Atomic radius, okay, that increases from top to bottom, okay, and also from, let me move this really quick, also from right to left, okay. So this is just essentially the size of the atom, right? This one right here, what element is this?
Francium.
That's francium, okay? That's the biggest, fattest element on the periodic table, okay? It increases from top to bottom because with every subsequent energy level, that energy level is being added on top of the one before it. So it's like if you were layering your clothes, okay? You get up in the morning, you put a shirt on. and then you put a sweatshirt on, and then put a jacket on, and then maybe you put some coveralls over all of that, okay? The more layers you have, the bigger you get. That's the same thing that's happening here, okay? As we go from right to left across the bottom of the periodic table, we see an increase in size, because these elements over here are holding their electrons in really, really tightly, and these ones don't hold, on the left side of the periodic table, don't hold their electrons as tightly. So these are really squeezed on the right side, and on the left side they're much looser held. So we see a little bit increase in size going that way. But I know, I'm sorry, yours are a little bit different, but I'm following the notes here. You'll be okay. Plenty intelligent to do it.
Are you sure?
Yes. Okay. So what you should know is that francium is the biggest. Okay, it's the chubby puppy. That's why I named my dog Francium. See? When I got him, he was he was 3 months old. He was huge, and he was really, really chubby. So, chubby puppy Francium. Okay. So that gives you atomic radius. Ionic radius. Ionic radius is something that we can see when we go back to our ions here. Okay, what happened to the size of sodium when it turned into a cation?
It got smaller
It got smaller. Why?
because it just lost the whole energy level.
Yes, very good, Bryce. As you lose that energy level, okay, the size of the atom essentially shrinks down. It's like pulling off a jacket. Okay, you get smaller. Okay, so over here, the chlorine, when it gained this one electron right here, it got slightly bigger. And that's because there were more electrons than there were protons. So the protons can't hold those electrons as tight when you add another electron, because they outnumber the protons. So they're a little more loosely held. Okay, so that's ionization. That's ionic radius. So ionic radius typically increases from top to bottom. And it depends, going across the periodic table, whether you're looking at a cation. For the most, or an anion. For the most part, cations get smaller, and anions get bigger. So this is a memory thing that I developed to kind of remember that. Giant ants and tiny cats. Okay, anions get giant. Cations get smaller. Giant ants, tiny cats. Giant ants and tiny cats. Thank you. So the only other trends that are on there are pretty darn easy. Okay, non-metallic character increases as we get closer to the side of the periodic table where the non-metals are. And metallic character increases as we get closer to the side of the periodic table that are metals. Okay? And that's it for the trends. So now I've gone over all the notes that you need in order to do pages 4, 5, and 6.
Is that what we're doing tomorrow?
Well, yeah, by the end of tomorrow we need to have that all done.
Of course.